In this video, we will take a quick review of carboxylic acid and its derivative, the chapter. Here I have already shown RCOOH and its representation of an acid like this, and I have also drawn a resonating structure of the carboxylic acid. Let's assume this distance is L1. I'm going to show something new, L1, L2. And this carbon is in sp2 state, it's planar carbon molecule, and this is its resonating structure. Okay, now let's take a look in both of these. Here we can conclude that this is length L1 and this is length L2, then L2 is greater than L1. It's because length of double bond is shorter than a sigma bond. And now I'm showing that how I have drawn the resonating structures. Here it's the therapy, R C double bond O. Here are the two lone pairs of oxygen and a negative charge which is shifted over here, and its equivalent is like this, will be like this. It's the way to draw resonating structure, and from these diagrams we can conclude as a general distance between carbon and oxygen as like this. Here is a double bond character, so I'm showing it with a dotted line, and this length is L1 and this length is L2, assuming, and from this figure we can conclude L1 is equals to L2, and both of oxygen will have a minus negative charge, minus half, as in this figure there is only negative charge in one oxygen, but now this is distributed in both of these, so we will put minus half and minus half. Okay, now I will help you to recognize that how we will take intermolecular hydrogen bonding and all of these type of things in this chapter. Now I'm drawing a carboxylic acid. I'm drawing in its expanded way to show you more precisely. Okay, and now look, these are the two carboxylic acid molecules, and in these are the two different molecules, so intermolecular hydrogen bonding will take place. Intermolecular hydrogen bonding. Okay, and now it will take place like this between these two, hydrogen and oxygen. Since these are the two molecules, two different molecules, that's why over here is intermolecular hydrogen bonding, and in intramolecular hydrogen bonding occurs within the same molecule. Now I'm showing a different example of this to you, like I'm again drawing a compound having carboxylic acid and will be its derivative also. Okay, I'm drawing it to all of them so close, so you will have an ease to recognize the difference between hydrogen bonding. Since hydrogen bonding occurs between the different molecules or within the same molecules, as we have already prescribed the name inter and intra, and here I am showing intermolecular. No, this is one molecule, this is another, and this is the third one, and in these molecules hydrogen bonding will take place like this. This is the hydrogen bonding, and by this way this compound gets bigger and bigger and bigger. Okay, and now I will show you a quick adapt thing, so that you can differentiate between the carboxylic acid having amine derivative and normal carboxylic acid and a methanol. Now I will ask a thing, that in which of the following compounds, in which of these three types of compounds boiling point will be highest. Now here is the key. Amine's carboxylic derivative has highest boiling point. I'm just going to show the reason to you. Highest boiling point will be of amine derivative. Okay, and the reason behind this will be, if we draw a derivative of carboxylic acid containing amine, okay, and a derivative with a 2-degree amine and one with 3-degree amine. I'm showing the explanation of this thing by this method. This will be more suitable to you since you will directly look at the things. And the reason for heavy hydrogen bonding in this thing 1 degree amine is because there are hydrogen and hydrogen, two different hydrogens which can interact with two different molecules simultaneously. And in this there is only single hydrogen which will interact with the other one, and in this compound there is none of the hydrogen which should contribute in intermolecular hydrogen bonding. So by this therapy we can say that the amines 1 degree amines will have highest boiling point. And this same explanation lies over here. Here are the two hydrogen, here it's single, and here is single hydrogen. Okay. And this is the reason for hydrogen bonding, and we have already seen that hydrogen bonding occurs between fluorine, oxygen and nitrogen. Most highly electronegative elements are predictable when are near to hydrogen. This will represent hydrogen bonding. Now, okay, and I'm now going to show something different to you. Assume this is an acid. This is some different type of acid. You can say it's a part of carboxylic acid, though obviously it is. Now, if we take dissociation constant of acid Ka1 for the first time, that's why I'm denoting a smaller one in the subscript over here, Ka1, then it will give CH2, C double bond O minus, C double bond OH. Okay, and now for one more time, I'm going to take its dissociation constant Ka2 for the second time. Then it will release something like this. Here is already negative, and the hydrogen, this hydrogen will also be removed. Okay, so then here we can say that in the same molecule there are two negative charges, and due to the two negative charges, two anion on the same molecule, energy of this compound will be more than in comparison to this. That means energy of this will be greater, and the reason behind is due to two anion, or rather negative charge on same molecule, energy increases. This is the reason. I have just shown you this thing. There is no particular use of this type of things, but could be used in any type of questions regarding MCQs. Okay, now I'm going to prepare a chart regarding some of the famous reactions of this chapter, and including the chapters of aldehyde and ketone. Some of the reactions will be from aldehyde and ketone, as you have already studied. And this chart would be a Herculean task to draw. Just I'm drawing. Okay, it will take almost 5 minutes to complete this chart. This is the base. I'm showing you that how different type of reaction, how you will create carboxylic acid. So from here, first reactant we will take is CH3, CH2, CH double bond CH, CH2, CH3. Okay, here this is the compound. Now if we take a look, I'm putting the arrow of the reaction as usual. And now if we treat this compound with hard KMnO4 and strong oxidizing agent, hard KMnO4, this will give carboxylic acid. And if we also treat the same compound with oxygen and doing hydrolysis of that, this will give carboxylic acid. Look, this chart will be a very good thing after it will be completed, and it is a big one, so it will be an Herculean task to complete within a fraction of minutes. CH1C, CH2, CH3. Now this is another compound. Similarly, if we treat this compound with hard KMnO4 and oxygen O3 and H2O, this will give this carboxylic acid. Now here's something new I'm showing to you. This is CH3, CH2, CH2OH, And if we treat this with K2Cr2O7, that means potassium dichromate or Na2Cr2O7, sodium dichromate, or in general we can say when treating an alcohol with chromic acid, will give carboxylic acid. Okay, and now some reactions from this side I should also write to counterbalance the page. CH3CH2 MgBr. This is a RMDX type of compound, and if we treat that type of compound with carbon dioxide in presence of acidic medium, this will give carboxylic acid. And another reactant will be CH3CH2 C triple bond 1. It is a nitrile, and if we treat this type of nitrile with hydrolysis H3O+, then this will lead to carboxylic acid. And now I'm going to take an ester. Look, this chart will look very beautiful if we draw in a big page, and it will help in to recognize the reaction. It will be very helpful to recall the reactions within the time. And if we treat ester with hydrolysis, it will give carboxylic acid. This is nitrile, and this is Grignard reagent. Oh, I'm not writing order. Let's you can treat the RMGX type of compound. Okay, and now you have also heard of the name Arnold ester reaction, and I'm taking its reagent as CH3COOH. Okay, and if we treat this compound with 3 reagents, firstly treated with SOCl2 for chlorination, second is CH2N2. This is taken as 2 moles since it's a deuterium ion, negative charge over here and positive over here. Deuterium ion is the ion in which a molecule, if in a molecule, within a molecule there are simultaneous positive and negative charge, and in the heteroatom, then that type of compound is known as deuterium ion. And the third thing is hydrolysis. And if we treat this with all these 3 reagents, then it will lead to carboxylic acid, and this method is known as Arnold ester reaction. Arnold ester reaction. Okay, now if we take another thing like anhydride, CH3CH2 C double bond O CH2 CH3. This is an anhydride, and another reagent I'm taking as CH3CH2, an amine derivative of carboxylic acid, and another thing is CH3CH2 C double bond O Cl and acyl halide. If we treat all these 3 with hydrolysis, if we do hydrolysis of all these 3 compounds, okay, now if we treat all these 3 compounds, anhydride and derivative of amine and acyl halide, with H3O plus hydrolysis, this will give carboxylic acid. Okay, now I'm taking another type of compound, which is something like this: CH3 CH2 C double bond O CH2 CH3. Then if we treat this compound with HiO4, okay, HiO4, then the cleavage of this bond, sigma bond, will takes place, and it will give to carboxylic acid. It will form 2 moles. Okay, now some of the new different reagent will be, if we take aldehyde from the chapters of aldehyde and ketone. Aldehyde when treated with peroxy acid. Aldehyde when treated with peroxy acid. Peroxy acid. Then peroxy acid will look like this something. This is the peroxy acid. And this reaction is known as Baeyer-Villiger oxidation. Baeyer-Williger oxidation. That means aldehyde when treated with peroxy acid forms carboxylic acid, and if we take another ketone on treating with bromine, that means 3 moles of bromine, Hoffman bromamide reaction it is, 3 moles of bromine, 4 moles of NaOH and H plus acidic medium. It is haloform reaction. Sorry, I have said that it was Hoffman bromamide gives 1 degree amine. Sorry for inconvenience. This is haloform reaction. And if we take another aldehyde, CH3CH2CHO, and if we treat it with silver nitrate AgNH3 plus, that means tolerance test, and NO3 minus, it will give carboxylic acid, and this reaction is known as tolerance test. This is tolerance reagent and this process is tolerance. This is tolerance reagent and this process is tolerance test. And again, if we treat an aldehyde with Cu2 plus comma hydroxyl, this is Fehling solution, and this reaction is Fehling solution. So this is the chart. For the quick review of the chapter, it combines previous chapters also, phenols, aldehyde, ketones, and there's some new reactions of the carboxylic acid. Okay, now if we go further, we'll describe some of the new reactions which I have already showed you in the chart, and among them first comes in the series is carbonation of Grignard reagent, the one which I have prescribed in the top right corner of the chart. Carbonation of Grignard reagent. Okay, now let's take RMGX. On treating with carbon dioxide in acidic in presence of hydrolysis, it will give something like this according to the delta positive and delta negative nature of or Grignard reagent. And if we further hydrolyze this compound, it will form a carboxylic acid. This is carboxylic acid. Okay, and the second reaction in the series which I have already described in chart is hydrolysis of nitrile group. The second in the top right corner of the chart. C triple bond N, this is the short notation of nitrile. This is nitrile. On hydrolysis of nitrile gives 1 degree amine derivative of carboxylic acid, and on further reacting, that means tautomerism occurring in this place, it will give C double bond OH carboxylic acid plus NH4 plus ammonium ion. Okay, here tautomerism takes place. And the next reaction in the series will be Arnold-Easter reaction, which I have shown on the right side, obviously in the center of the chart. These are some of the new reactions which we are studying in the chapter carboxylic acid, and the further chart contains the reactions from previous chapters. Arnold-Easter reaction. In this reaction, we will take carboxylic acid when treated with 3 of the reagent. As I have already written these were there in the chart. SiCO2, CH2N2, 2 moles will be required in this reaction, and in the last we will treat the compound by H3O plus, or we can also hydrolyze this compound in presence of Ag2 plus O minus, and it will give CH2 COOH. This is the Arnold-Easter reaction. And now we will take a look on some chemical properties of the chapter. Chemical properties. Chemical properties of the chapter. Let's take a look. This is a general carboxylic acid, and if we take a look in this carbonyl bond, this is the acylium carbon atom. This is known as acylium carbon atom. Acylium carbon atom. That means nucleophilic substitution and addition and elimination will takes place over this carbon. Let's take. I'm explaining in deep. This is, assume this L for the leaving group, okay, and oxygen will have partial negative and carbon will have partial positive, and this is sp2 carbon, and assume this is a leaving group, and nucleophile with negative charge is coming. Nucleophile with negative charge is gonna attacking this compound over here, carbon, and the rate determining step will be the first, that means addition of nucleophile and removal of leaving group. It will form something like this. Nucleophile comes, this negative will come over here, this leaving group will be removed, and this is the sp3 carbon atom. This is tetrahedral intermediate, and on further reacting it will give RC double bond and U. And some of the leaving groups, some of the best leaving groups can be taken as hydroxy, halogen, amine, anhydride type something, ester. Okay, these are some of the best leaving groups, and some of the examples of this reaction will be C double bond Cl when treated with nucleophile. Any nucleophile you can take, it will give RCO minus NCl, and it will form RC double bond NU plus Cl minus. This is an example for this reaction. And the rate of nucleophilic substitution at acylium carbon atom will be increased if the net positive charge in this carbonyl carbon atom is more than its rate towards nucleophilic substitution at acylium carbon atom will be more. That means that we have to use such type of leaving group which will create more vacancy in this carbon. That means more and more positive charge will be produced over here, then in the best manner, best yield can be provided from this reaction, acylium carbon atom. Okay.